Hello, everyone. I'm Liu Guang, and from BAI. I'm very happy here to introduce our project, OpenSeek. This project is like to reproduce or build a next level AI system. As we know, DeepSeek has opened his modern ways, but did not open source his data, his framework, and other things. So how to, you can think OpenSeek will share the tool, data, and models we use to train AI models. You can think like share a recipe of great cake so that more people could try, improve, and create their own recipe. In OpenSeek, we work as a team with different working groups, major 3 different working groups. First is the data group. We are building more high quality data. And the second group is the infrastructure group. We are working on training the model more frequently, more easy. And the third group is the algorithm group. We are improving the training strategy and the model structure. So this is not the new idea from the collaborative training models. First, we are inspired by the big science. The big science project. And so at a very early stage in February 2025, we are start to build some basic data collaboration connection and building the basic training system. And here we have some achievements on our project. So we have built a very large-scale, high-quality bilingual data set and open source all the data sets today. We call it CCI China Corpus Index. Although it is named China, but it has 2 different languages, English and Chinese. So this is M2 version, so 2 language support. We want to expand its language support to multilingual. This first dataset has 2.4 trillion billion tokens. So at the size of 14.5 GB, 14,500 GB. So also we release a small version of OpenSeek. We trained on this dataset to verify the effects of our high-quality dataset. So we named the OpenSeek small version 1. It's a very, very tiny model, but has a DeepSeek V3 structure. Is a MOE model. Is 1.6 billion parameters with only 0.6 activation. So it's a very tiny model that can allow more people to train this model or to play this model or fine-tuning or pre-training on our data sets. So for better use this information and this data set, we release the pipeline, including 100 billion data sets and the framework to train the model and also evaluation benchmark. All the tool sets are open sourced on our GitHub. And this is the stage 1. We think we have prepared to allow more people to join our project. And also we are launch some competitions that allow 3 different group contributor on these 3 different groups can train the model to improve the data quality and also can train a large size model together. as Joseph said, we are inspired by the project Big Science. It has a very large impact and is a bigger project and have over 13 working groups. And they are trained a large model land a balloon and build a large-scale data sets rules. We want to follow or using different working groups to organize all our project. As we said, we have different working groups. First is the system group. They are focused on improve the training framework that support DeepSeek V3-like structure models. So to better understand how to build strong AI models, let's take a quick look at the DeepSeek, which has used many advanced technology like the MOE, fine-grained MOE, MLA, MTP, FP-PAR training, and the dual pipe training strategy. Now we train our models on the framework, also open source framework Lambda Flex Scale. It supports efficient and large scale AI training, just like training DeepSeek, like the DeepSeek models. Also, we support many important features like the MAA for long context support, MOE for the expert routing, and multi-chip training and compatibility with Hugging Face tools. Next, we will support FP-PAR training and dual pipe and making our training more efficient. Next, we will introduce our project on the data working group. Building on the idea that data efficiency is the key, we can see that as the X-ray is the tokens trained on each different models. You can see DeepSeek have trained 14.8 TB token on text modality, and Llama 4 have trained 22 billion tokens on multi-model data. Although the Llama 4 have trained more data, but it achieved on performance compared to the DeepSeek V3. So we can call the DeepSeek have more data efficiency. So the major difference we analysis is that they have more have better data quality, so they train more efficiently. Also, the training data has also a very large scale and high quality pre-training data sets. If we want to reproduce the DeepSeek V3, we have to make a similar large scale high quality data set. So we build this CCI4 dataset and release today on Hugging Face. It is composed of two major parts. One is the basic majorly from the web page. It has English and Chinese web page, around 10 billion web pages. We have four correlation pipeline. First is the application. The second is the quality score with different multiple quality score to get a better and precise quality filtering. So we can get a clean data. And then we use synthetic data to generate a QA question and extract knowledge from the data. And then finally, we use a model to filter all the data grouped by different domains, because we think the language, the model can filter some noise from the data. The other side, the COT data is the largest synthetic COT-like data, because it has 430 million samples and approximately 425 billion tokens. That's a very large data set and spanning different domains, including math, code, and Wikipedia and archive. So this is, as we know, the first time we try to synthetic COT-like data on domains outside the math and the code. This is the overview of our data set. So majorly is from the web page. We named this EN or ZH web pages, around 18% of the whole data set. And we have 4% of COT synthetic data and 9% from code, math, and wiki. And this are a lot of upsampling. This is a huge pre-training data set with high quality. And from the English web page, we majorly based on the Limitron CC. This is a large data set released by NVIDIA. So with external operation, we use the language model to filter the data. First, we group this, classify this data into different domains, and we use a language model to filter the data, the loss about the 99.5% on each domain. Because we have analyzed the loss and the correlation between each domain and the loss distribution, we found that on different domains, the loss has different scales. So if we choose different percentage to filter this noise, we can get a better fluence on the language. Also, we have performed a very small experiment on this dataset before filter and after filter. We can see with after filter, the performance can have a little gain compared to the non-filtering data. Also, we perform similar operation on Chinese data, except the synthetic, because we will perform a similar operation in the future, but now, because of the short of time and resources, we only perform 3 operations on Chinese dataset. Similarly, we achieve better performance than the previous unprocessed Chinese dataset. These experiments are carried on a very small model with 500 million parameters, and the trend is 10 billion tokens. As we know, the Chin-channel scaling law says that the model can trend with 20 times of its parameter data samples. So we under this setting, we carried a different experience. As the second part is the reasoning data. We call it CCI4 M2 COT. This is motivated by 3 different papers. They suggest the reasoning ability is sourcing from the pre-trained stage. So we have to build complex human reasoning trajectory in the pre-training stage. So how to do this is the major problem we want to solve. We have built a very simple and very simple COT template extraction method. We want to extract the human thinking trajectory from the original text. That's because when human write a document or web page, they have a lot of think behind this writing. So we use a pipeline to extract the thinking trajectory behind the web page to make the model can understand how to write, how to solve problems. This is the example. First, we break down raw text into small pieces, and then we extract the major summarization, major sentence from each piece, and then we organize all this sentence into a COT trajectory. So this all performed under 32 billion Quen 2.5. So it's a large model. And we use this pipeline applied on different domains, and like math, code, archive, Wikipedia, and web page. So finally, we connect about 415 million COT synthetic data. That's a huge data, and the major problem is we have the data, but how to verify its effects, how this data can help the model reasoning. So we built two different benchmark or evaluation. First, we call it single stage evaluation. We just use this data to fine-tuning the base model, like Llama 3.1. So after the fine-tuning, the last line of this experiments, we can see it definitely have some improvements to help the base model to solve math problem. This experiment is carried on about 1 million data. So the question with the COT data combined together can help the model solve better math problems. Besides, we also perform two-stage evaluation. First, we perform the SFT on our data and the data from the paper, and we compare the effects of our data and the data synthetic for human recognition behavior. So after the comparison, after the fine-tuning, and we using the GRPO to train the model to solve the problem and evaluate on a very simple quiz question. So quiz task, and this is the result. The first chart shows the model fine-tuned by our synthetic COT data can achieve higher mean accuracy. And the length is also have a longer thinking length. And the score of test on counting down task also achieve a higher accuracy. So that shows our data can help or outperform the data released in this paper. But differently, we not only have 100K samples, we have 4 115 million samples. So that's a very large scale data set. So how to use that and how to evaluate that, we will continue working on this. The third group is the algorithm working group to improve some data mixture and the model architecture and the training algorithms. First, like 5.4 is a model released by, proposed by Microsoft. So they have used a large scale synthetic data in the pre-training stage, as shown in the left table. We can see that most data are synthetic data, like web rewriters and synthetic and some other different method. About 15% of the data, pre-training data, are synthetic data. So the major ideal is to improve the proportion of the synthetic data. So we have carried on experiments. As shown in the yellow curve, you can see that after upsampling the synthetic data, we can train more stably. And with this no spike, we know that no spike is harmful for the model training. So under this experiments, we can see that model data mixture have a very large potential to explore. Maybe different mixture proportion can help the model train better. We can see the evaluation results on the benchmark that help the model improve 2% on the about 10 different benchmarks. Also, we have different. We tried different settings before training. For example, the initialized method. We use the smaller deviation to initialize all the model parameters, and we get better training curves. So it has lower loss through all the time. Also, we found that the D type of the rotor, like MOE, have rotor layers. If you use FP32 to setting our rotor layer, it get a better training accuracy and lower loss. And if also the training actually loss, the setting with lower, similar like this setting, we help get a better training curves. And besides, the MTP coefficient we set is we add this coefficient, it will help stabilize the training and help the model achieve better performance. After combining all 4 different tricks together, we can achieve 16% improvements on downstream tasks. That also have a lot to explore behind all these training strategy improvements. After explore different, after we build up a large scale data sets, CCI4, and do a lot of experience on training strategy and data mixture, we carry on a small experiments on training a small model named OpenSeek small. So we can see the training results as shown in the table, but also we can draw this, compare this performance with same size models using the T-flops used and the performance, average performance. You can see that the line is curved to show the correlation between the T-flops used in the training, in the model training, and the performance. They are almost scaling in the line. As the almost 1 billion, Guang 0.0 billion, 0.5 billion, and the Llama 3 2.1 billion. They are almost the performance almost scaling with the log linear algorithm, the T-flops. So as our model is have a better scaling attitude or scaling in other words, it has better data efficiency. It can train our model more efficiently. And another release is about the pipeline. We have released our data, our code, our benchmark, and our baseline results. As we call this baseline pipeline. This pipeline can be operated, can be run on a device less than 40 gigabit RAMs. So I think a lot of people can join this project and to run this experiments by themselves. We want to build up this pipeline for let more contributor can join this project to make their contribution to improve the model training and the data quality, the algorithms. And also we release a baseline version of this pipeline. We trained this very small model using 100 billion token data. And this is basic settings. So if anyone can improve the results against our baseline, you are welcome to propose a PR on our GitHub. Now we can evaluate these improvements on large scale model training. This is currently our status. We are 3 different working groups: data, system, and algorithm. And also we have a WeChat group. This is a QR code. If you're interested, you can join the WeChat group. And also we have 3 bi-week meeting. Each meeting we have record all the videos and make it public. So we talk about the model training status and what we will do on the next. So this is OpenSeek. Thank you.